Okay, now for what we have at this stage of the game, okay, we're looking at systems of differential equations. And we'll say that we have a system of two equations where we are looking at solving for x of 1 and x of 2. And we have with the equations, we have the first order derivative of x of 1 of t is equal to 2 times x of 1 plus 5 times x of 2. And the first order derivative of x of 2 with respect to t we have is equal to x of 1 minus 2 times x of 2. And we're looking at the expressions for both x of 1 and x of 2 where we have the differential equations will coexist and ring true, and that will work for both equations. And we have in the setup in terms of establishing eigenvalues and eigenvectors, okay, we'll have assigned a variable a, which would be in reference to the coefficient matrix. First column we have for the coefficient of our x of 1 terms. Second column we'll have to consist of the coefficients of the x of 2 terms. So we have 2 and 1 for the first column, 5 and negative 2 for the second. And so we have A to be a 2 by 2 matrix, and we're going to assign an identity matrix, which we will have as consisting of the number 1 to run diagonally, and this will be among zeros. And now, looking at establishing the eigenvalues, so we're going to start out with a determinant, where we have that of a minus lambda I is equal to 0. And if it's been a while since you looked at determinants, we have first of all for a minus lambda I, we'll be looking at matching position wise. Just looking at it column by column, row by row. So we have first column, first row from both a and I, so we have 2 minus lambda times 1. First column, second row, we have 1 minus lambda times 0, which will still be at 1. And then we have in the second column, first row, we have a is at 5, and we have minus lambda times 0, so we have locked in at 5. And then we have second row, second column, we have with a minus lambda I, we have negative 2 minus lambda times 1. And we have is equal to 0. And looking at taking what we have in the diagonal products, and I'll just extend this out a bit. So we have, first of all, we have laying out what we have here. So we have 2 minus lambda, and 1, 5. We have negative 2 minus lambda. And looking at establishing what we have for the determinants. Again, just reassigning these arrows as indicators. So we'll be looking at first diagonal we have going from the upper left to the lower right, and take the product of 2 minus lambda and negative 2 minus lambda. And then we will have taking the other diagonal, which we will be deducting the product. In this case, so we have minus 1 times 5 is equal to 0. And looking at what we have in establishing. So we have 2 times negative 2 is negative 4. Then we got minus 2 lambda plus 2 lambda will go out. We have plus lambda squared minus 5. And we have is equal to 0. And here we have lambda squared minus 9 is equal to 0. And looking at factoring, and it doesn't matter what order you place these. So we have lambda minus and lambda plus 3 is equal to 0. And we have with the 0 product property, let's say that lambda 1 will be the 0 of lambda minus 3 set equal to 0. So we'll say we have lambda 1 is equal to 3. And for lambda plus 3 is equal to 0, we have this to spin off the second eigenvalue in this case, which is going to be at negative 3. So we have what we refer to as the eigenvalues. Okay, and you could have lambda 1 equal to -3 and lambda 2 equal to +3. All right, now for what we have upon utilizing the eigenvalues, okay, and we have just for the next phase, okay, and we're going to have in the development, okay, now we're going to have a situation where we're looking at, we have the matrix, we have A minus lambda I times what's going to be an eigenvector is equal to 0, and let's say that for, again, for lambda 1 equal to 3. Okay, so just kind of going back to what we have here. So if you look at what we have from the determinant stage, just a little bit of correspondence that we have here. Just okay, so we got for lambda 1 equal to 3. So we have 2 minus 3 is -1. We have 5. We got 1. We have -2 minus 3. Okay, so this is going to be a -5. And we have just for the eigenvector, okay, we'll just assign a 2 by 1 matrix. Okay, we'll just have we say we have A of 1 and B of 1, and again we have is equal to 0, and we just have this as a 2 by 1 matrix as well. And just for what we have when we're looking at solving for A of 1 and B of 1, and just looking at what we have for the corresponding parts here. Okay, just kind of taking what we have for multiplying matrices. And we'll just say we have, it could be mapping 1 with A of 1 and -5 with B of 1, but we'll just go this route. And here we're going to have that negative A of 1 plus 5 times B of 1 is equal to 0. And just looking at what we have in the relation, if I move A of 1 over, we have 5 times B of 1 is equal to A of 1. And from this, okay, so A of 1 is going to be 5 times greater than B of 1. And for what we will have in the case of the first eigenvector, and you can assign an infinite number of terms, but where possible, I'll go with low valued natural numbers as much as possible. Okay, and so if I have 5 times B of 1 is equal to A of 1, we'll say that B of 1 is equal to 1, and we have 5 times 1 is going to be A of 1, which will come out to 5. Okay, and it could be something like 10-2, but just to keep everything in proportion, like a 5-to-1 ratio, we'll say the first eigenvector, okay, we're going to have it 5 and 1. And now, just for what we have in the crossover, and working with what is going to be regarded as the second eigenvalue, and establishing what will be the second eigenvector. So again, we have lambda 2 equal to -3. So we have 2 minus -3. So we're going to have it 5, 5, and we have 1, and we have -2 minus -3, so it'll be -2 plus 3, which will be 1. And we have for the second eigenvector, we'll just designate it as A of 2 and B of 2, and the representation for what we have here, okay, so you have 0 and 0, and just mapping together. I'll just go here And I could have worked with 5a of 2 and 5b of 2, but just working with the second row from the first matrix. Say I have a of 2 plus b of 2 is equal to 0. And so for what we have in this case, we say that b of 2 is equal to the negative of a of 2. And so we have, in the case of the second eigenvector, okay, so you have v of 2 you have is equal to a of 2, b of 2, and okay, and we'll say that with b of 2 being the negative of a of 2, we'll say that a of 2 is going to be at 1 and b of 2 is going to be at negative 1. Now you could have it the other way around with negative 1 at the top and 1 at the bottom, because that would still ring true. Now, okay, so again we have the eigenvalues, the eigenvectors. Now, for what we have just collectively, now we have for x of t, we're looking at what's going to be a constant times the eigenvector times e to the lambda times t. Again, lambda will be in reference to eigenvalues. And just for what we have in this particular case, all right, so we're going to have for x of t, and now we have, again, two eigenvalues, two eigenvectors, so we'll just say we have c of 1, v of 1 times e to the lambda 1 times t. We have plus c of 2 times v2 times e to the lambda 2 of t. Okay. All right, and again, so we had with the first eigenvector, okay, that was 5 and 1. And lambda 1, again, that was at 3, so you have e to the 3t. We have plus c2. Second eigenvector, we have 1 and negative 1, but you could have it as negative 1 and 1. And we have times e to lambda 2 times t. Lambda 2 we have at negative 3. And what's going to happen here is that for what we're going to have for x of 1 of t, we can take the top layers. Again, you see we have x of 1 of t, that's going to be equal to 5 times c1 times e to the 3t. And we have plus c2 times 1 times e to the negative 3t. And for x of 2 of t, just taking the bottom layers, as you have c of 1 times e to the 3t. And we have c2 times negative 1, so we can say we have minus c2 times e to the negative 3t. And so that would be the outcome for what we have in this particular system. And this is just one representation